MongoDB. My name is Donchovski. I come from Skopje, Republic of Macedonia, Southeast Europe. I have a master's degree in software engineering. Initially started working as a web developer and DBA, then moved as database consultant for Pythian. And since 2016, I'm working as a lead database consultant for Pythian. Also, since 2016, I am a MongoDB certified DBA. Brief overview, what we will be discussing today, what is HA and how MongoDB achieves HA. Then we will move into replica sets, components, and deployment topologies. Then we will move into scaling, vertical and horizontal. What is a sharded cluster in MongoDB? What are the cluster components? Shard keys and chunks, hashed versus range-based sharding. And then we will discuss about sharded cluster backups and upgrades. At the end, we will have Q&A session. So let's start with HA. HA stands for high availability and refers for systems that are durable and likely to operate continuously without failure for a long time. While this diagram may look like some development setup, I've seen setups like this running in production, and with setups like this, as you may notice, we have single points of failure. Single points of failure means that if some part of a system fails, then it breaks the entire system. And this is not something typical that we would like to run in a production setup. How do we improve HA? There are two parts. One of the HA parts on the application layer, and the second part is on the database layer. So some of the questions that come when we are doing HA on the database layer, that it's not as trivial as on the application layer, where we add multiple application servers in front of a load balancer, and then the load balancer just splits the requests via round-robin fashion to the application servers. With the database layer, we typically have one primary server that accepts the write requests, and then we need to have more than one copy of the data, which is usually as a replica set node. So the balancer needs to know what is the primary node where the write request will be sent, what are the replica set nodes, if we want to read from the replicas, or in some cases we may just want to direct both write and reads to the primary node, and the replicas will be there just for a failover. So how trivial is if application server goes down, that our application will notice that, and how that affects our setup. How trivial is that we fail over our database primary node to the replica set, whether the application will experience downtime or there will be nothing in the application there, it just continues operating without any downtime. With MongoDB, this is resolved with replica sets. With MongoDB, replica sets represent a group of MongoDB processes that maintain the same data set. The application is connecting to the replica set via driver, and the driver is has replica set awareness, which means if our replica set has 3 nodes, the driver knows what is the current primary node, what are the replica sets or the secondary nodes, so that all writes go to the primary node, and we have options whether we want to read from the primary node, or we can say that we want to read from a secondary node. So replica sets provide redundancy and high availability. With a replica set, we have increased read capacity, which means that now we can decide to read from secondary nodes. And with MongoDB, the failover is automatic, which means that we don't have to worry if our primary node goes down. The replica set starts election, and there will be a new secondary node elected as primary node without the application even to notice that. So how does the replication concept in MongoDB works? By default, and that's not by default, all the write operations from the driver go to the primary node. The primary node records all of the changes into operations log or op log, and that's kept collection with fixed size that is idempotent, which means each time we execute the operations log on the node, at the end we will have the same result. All the changes are asynchronously replicated to the secondary nodes, and the secondary nodes also copy the primary op log to its own op log. And now that allows us to use sync source another secondary, so secondaries does not have to replicate from the primary directly, but we can use sync source another secondary, and that's true by default. It's configurable, and we can change this setting if we like. Some of the configuration options for replica sets are that we can have maximum of 50 members per replica set. 7 of those can be voting members, which means that in case a primary node goes down, then 7 of the nodes start election and will elect new primary node. There can be arbiter node, priority 0 node, hidden node, and delayed node. If you want to set up high availability with replica sets, but you are happy with only having primary and additional copy of your database, then the third node can be arbiter node that does not hold copy of the data and only participates in elections. And this is useful also if you have split your copies of the data into multiple data centers. So if you have 2 data nodes in data center 1 and 2 data nodes in data center 2, in case one of the data centers goes down, the other data center cannot elect new primary because it does not have a majority. And with MongoDB elections, new primary node to be elected, you need to have majority of the nodes participating in election, so a new primary node will get elected. In this case, you can add arbiter node in third data center so that you have high availability across multiple data centers. Priority 0 node is secondary node that does not participate in elections, cannot trigger election, and it's always a secondary node. This node is visible to the application, and when you send requests from the application to the driver can send read requests to the secondary node, which is priority 0 node. Hidden nodes are also priority 0 nodes, but the driver does not see this node. So if you have 5 members replica set, the driver will only see these 4 members that are not hidden. However, you can use this node for running reporting queries directly to the node, or you can utilize hidden nodes for taking backups. Delayed node is also priority 0 node. It should be hidden, but it's not mandatory because it represents previous state of the data. And this node is also always secondary. It's useful to have a hidden delayed node in case you run erroneous operation, like you delete some data from a collection and later you want to retrieve the data. You don't have to restore the data from backups, but you have this delayed node from where you can get your data as it represents earlier state of your data. So let's move into scaling. First, let's discuss about working sets. A working set is the amount of memory that a process requires in a given time interval. And with databases, working sets can vary. The working set for a database is the piece of memory that the database requires at a given time, and that may change as your application queries may change over time, but it doesn't change in a magnitude of gigabytes. It may change in a magnitude of megabytes over a single day. Other than the working set, your application is also storing, your database is also storing the indexes into memory. So as your database grows over time, both indexes and the working set will grow. So at one point, the indexes and the working set will outgrow the memory on your server. And that's usually the time when you need to scale. The two options for scaling, and that's not only MongoDB related, but it's for any database, you have option to scale vertically by adding more RAM or more powerful CPU, faster disks to the existing machine. However, this might require downtime while upgrading your driver, your hardware. And also, the other option for scaling is scaling horizontally by adding multiple machines into your pool of resources and partitioning the data on those multiple machines. By horizontal scaling, you are parallelizing the processing. And this is usually more complex to implement. Vertical scaling is more expensive than horizontal scaling, and we can see from this table some of the cost compared between running 70 CPUs on a single server or achieve that processing power or multiple servers, and also the vertical scaling for a single instance just by doubling the amount of CPU and RAM memory scales almost exponentially. So let's move with scaling with MongoDB. Scaling with MongoDB, also called sharding, is where you split the data horizontally across multiple shards. As we already discussed about replica sets, and this is very important to keep in mind when sharding, each shard in MongoDB sharded cluster should represent a replica set. Each shard in MongoDB sharded cluster is having a unique piece of the data so that you're not having your copies of data across multiple shards, but each shard represents a unique copy of your data. To have sharded clusters with MongoDB, obviously we need somewhere to store our metadata, so we know how our data is partitioned across those shards, where we have our data. And then we have additionally interface to the sharded cluster, and that's called mongos or query router. Summarized, sharded clusters have the three pieces: shards, which should be replica sets for high availability, config servers, where we store the metadata and config settings, and we have mongos, which represents the cluster interface. The application is connecting from the driver to the mongos, and mongos is routing the queries to the particular shard where we are sending the request. As long as we have this setup for a sharded cluster, adding additional shards for MongoDB, and that's scaling horizontally, is trivial as running the command sh add shard and the shard name. So if we have our setup initially and we have sharded cluster running, then scaling horizontally is very trivial. Let's look at each individual piece for a sharded cluster. Sharded clusters store all of the data into multiple shards. The shards contain subset of the data, and each shard has a unique piece of the sharded data. There is no copy of the data between multiple shards. Each shard should be a replica set to provide redundancy and high availability, and it can be one of the setups for replica sets that we already discussed. Each database in our cluster is bounded to a primary shard, which means that when we create a database in a sharded cluster, then the cluster assigns some shard to be the primary shard for that database. The database is not yet sharded, sharding is not enabled, so the database lives on one of the shards in our cluster. Inside the database, we have non-sharded collections, and those collections also live in the same shard as the primary shard for the database. If we enable sharding on a particular collection, then depends of the shard key that we will choose, that collection is only sharded across multiple shards. The rest of the collections that are not sharded still reside on the primary shard for the database. And that's important because the data is not sharded automatically. We decide how to shard the collections and on what shard key it should be sharded. The config servers for a sharded cluster store the metadata for the cluster in a config database, and also in the config database we have the information for authentication, and that's stored in the admin database. Starting from MongoDB 3.4, the config servers also run as replica sets for high availability, and also since MongoDB 3.4, config servers hold the balancer that is a process that balances the data between the shards. Before MongoDB 3.4, that process was running on a MongoS. And the third part of a sharded cluster are MongoS processes, which is caching the metadata from the config servers, and it's routing the queries to the shards. The driver is communicating with the sharded cluster through a MongoS, and MongoS is updating the cache from each metadata change that happens on the config servers. So it does not have a persistent state, but each time there is a metadata change, MongoS updates its state. As we mentioned in the previous MongoDB versions, MongoS processes were also running the balancer that balances the data between the shards. And starting from MongoDB 3.4, MongoS process cannot connect to earlier version of MongoDB, which is important if you are doing sharded cluster upgrades, which we will mention later. So let's move into actual example, how do we shard a collection? Before we do that, let's just compare what is the terming and methodology in MongoDB compared to the SQL databases like MySQL, Postgres, Oracle. The term database is same for MongoDB and the SQL. In SQL, what we have as a table in MongoDB is referred as collection. What we have as a record or row in SQL in MongoDB, it's called document. So to start with sharding and shard a collection, we need to enable sharding on the database level first. In this example, we have database users. We enable sharding. The next step is to shard a collection, and that's also trivial with running the command sh shard collection, providing the namespace, which is database.collection name, and then the shard key. The shard key is an index key that must exist in every document in the collection, and we have two types of sharding with MongoDB. The first one is range-based, where we shard by ranges of the shard key, and the second type is hash-based sharding, which we shard the data based out of a hashed index on the shard key. So let's take a closer look. How does range-based sharding work? With range-based sharding, we are dividing the data into continuous ranges determined by the shard key values. In this example, if we have values for the shard key x, the first range starts from x being the min key, the next is defined by some value, and then in ranges, the last shard key in the range will be the max key. With this type of sharding, it's more likely that the shard key values that are close will be in the same chunk or shard. So if we have, for example, this chunk 3, living on shard 3, if we have a range query that is trying to find records between 50 and 60, it's more likely that our application will query only shard number 3, because MongoS will have information that all the documents are in chunk 3 and the query will be routed directly to that shard. And this is called query isolation. With hash-based sharding, the application, the database is using hashed index of a single key, and that's used to partition our data. When we provide the values, the database automatically calculates the hashed function, the hashed value. With a hashed function, our application does not need to calculate the hash values. That's done within the database layer, and then based out of the hash value, the document will be stored into a particular chunk. As we can see from this example, documents with a close shard key value may end up into different chunks. With this type of sharding now, we don't know where our documents will end up into the particular chunks and shards. If we have a range-based query, for example, if you want to return documents where x is between 25 and 27, our query will end searching for those records into 3 different shards. And with MongoDB, this is called scatter-getter query. This is not something that you would like for your application if you decide to shard and query data. Hash-based sharding is mostly used for write-intensive workloads where you just want to shard your data and distribute the data on multiple shards. But if you want to also query the data and you want query isolation, probably the range-based sharding is a better option to do. So how do we choose the ideal shard key? And probably this is the time when you decide to shard where you will want to spend most of the time and decide what should be your shard key. Shard keys should have large shard key cardinality, and that means it should have huge unique values to be selected as ideal shard key. Additionally, the shard key should have low shard key frequency, which means that if you have shard key values between 1 and 1000, there shouldn't be many documents having the value of 100, or that will represent shard key with high key frequency. So those documents that represent shard key value with high frequency more likely will end up all on the same shard, and that will cause issues when your database will have to split your data and redistribute the data evenly across your cluster. For a range-based sharding, your ideal shard key should not be monotonically changing shard key, which is objects like timestamp or the underscore ID key in a MongoDB. For hash-based sharding, however, monotonically increasing objects like timestamps might be ideal for shard key option. The chunks represent a continuous range of shard key values within a particular shard, and the chunks have inclusive lower and exclusive upper range based on the shard key. By default, with MongoDB, the chunk size is 64 megabytes, but you can change the chunk value between 1 megabyte and 1 gigabyte. And the chunk size has impact about balancing your data across multiple shards. So if you have a larger chunks, it's more likely that some of the shards will have larger amount of the data compared to other shards. Some of the shard keys limitations are that it must be ascending index key or index compound key that exists in every document in the collection. Compound keys are only allowed for range-based sharding. Hash-based sharding can only have a single index key. Shard keys cannot be a multi-key index or a text index or a geospatial index and cannot exceed 512 bytes. The shard key is immutable, which means that once you decide to shard your collection on a specific shard key, then you cannot update that shard key and you cannot change it. Changing the shard key is possible, however, it may require downtime. If you are running update operations to a sharded cluster that affects a single document, you must include your shard key or you must include your underscore ID field to update that single document. If your collection already has a unique index and you want to shard that collection, the only possible shard key that you can have for that collection is your unique index. And once you shard that collection on the unique index, then you can no longer add second unique indexes for any keys into that collection. So that's also a limitation for collections that you want to shard. Some of the challenges that we have with sharded cluster setups is taking backups. One way of taking cluster backups is doing file system snapshots. Each operation that we run for a sharded cluster setups is limited with having the balancer process not running while we do the maintenance. And that's important because when we run maintenance for a sharded cluster, we don't want any data and chunk migration between the shards to be going on. We want that operation to be stopped while we do the maintenance. So for file system snapshots, the steps are that we stop the balancer. Each shard is representing a replica set. Taking backups of a replica set means that we can lock one of the secondaries, and that's for each shard and the config servers. Then we take snapshots for each replica set and config member, and at the end we unlock the secondaries and start the balancer. However, with this process of backups, we may not run a consistent backup which will represent a single point of time backup. Other methods for sharded cluster backups are that we take backup with MongoDump, which is a tool available with the Mongo binaries. And we can run MongoDump directly connected on the cluster interface, MongoS. But for a large dataset, this may take a long time. Another tool for taking backups for sharded clusters is using the Percona MongoDB consistent backup tool, which is still under development, and there are new versions released every month, improvements going over. If you are using MongoDB Rocks storage engine, there is a backup tool, RocksDB Backup, and another tool for taking backups for sharded clusters is using Cloud Manager Backup, which comes from MongoDB, and with that tool you will be required to pay some monthly fee depending how large your data size is. Your monthly fee will be smaller or larger. Additional challenges that we face with sharded cluster setups is doing upgrades. If your sharded cluster is running on a previous version of MongoDB and you want to upgrade to the latest version, your upgrade path must include all of the major versions in between. So if the current version of MongoDB is 3.6 and you're running sharded cluster or version 3.0, then your upgrade path will be 3.2, 3.4, and then 3.6. When doing sharded cluster upgrades, it's highly recommended that you take backups of your metadata on the config servers, because that's where all the information for your data is stored. If you need to roll back and you lose the metadata, then your cluster will be non-operational anymore. And additional thing when doing upgrades with MongoDB, and that's in general, not only for sharded clusters, but you must have a compatibility check and driver check. You must ensure that your driver will be working with the next version of MongoDB. And that's the first step that you would like to take before doing upgrades. The steps that you will take for doing sharded cluster upgrades include stopping the balancer, and that's always the first step when we are doing maintenance for sharded clusters. Then we upgrade the cluster metadata servers, the config servers. We upgrade shards, then mongos, and we enable the balancer at the end. So mongos nodes are last in the upgrade, because since MongoDB 3.4, if you upgrade a mongos nodes before you upgrade shard nodes, your mongos will not be able to speak to the newer version of the shard nodes, and you will experience downtime. So let's summarize about MongoDB replica sets and sharded clusters. When you run replica sets for MongoDB, always use odd number of voting members, because with MongoDB, where the failover is automatic and it needs odd number of nodes. When a node fails, it must have majority of nodes to be participating in elections and elect new primary node. If you have dedicated functions like reporting and backups, it's you have options to use hidden or delayed members. If your dataset fits into single server, and you can decide that by understanding what is your working set for the application. If your working set does not grow, or it grows in a level of megabytes, not in the magnitude of gigabytes, then it's probably the best to keep unsharded environment and just scale vertically by adding more RAM and CPU to the instances. Keep replica sets for your deployment topology. However, if you need to scale and your working set outgrows the RAM memory, your queries require faster CPU, and you need to parallelize the processes, you need to split the data across multiple shards, then horizontal scaling is the right choice for you. You need to add sharding into your environment. And when it comes to the shard keys, before you decide sharding, most of the time that you would like to spend is understanding your application queries, understanding what would be the best shard key for your collection so that you don't end up doing scatter-getter queries, or you don't end up for all of the queries being sent to a single shard. The shard key must exist in every document in the collection, so that's another limitation for the shard keys. When deciding on sharding with range-based sharding, your data may not be distributed evenly across the shards. MongoDB only distributes the data by managing the number of chunks evenly distributed in the sharded cluster, but each chunk may have a different number of records, so that you may end up with larger data set being stored on particular shards. With hash-based sharding, your data will be distributed randomly. So while you will end up with the data distributed more evenly across the shards, your data will be distributed randomly, and the cluster interface, which is the mongos, may send your queries randomly across multiple shards to retrieve the data. And last, while sharding splits your data across multiple machines and you parallelize the processes, it also adds complexity for maintenance, which are processes like backups and upgrades. And that's all. Thank you. So let's have a Q&A. Any questions? Yes? Yes. The limitation of the shard key is that it cannot exceed 512 bytes. And there is some correlation between the size of the shard key with how many chunks you can have, how many splits of the data you will have later when your data eventually will get split across multiple shards. So there is a correlation, there is a formula about that, but the smaller the shard key means that you cannot have multiple number of chunks. And that will limit you with the number of shards eventually when you want to shard your data. So yes, there is some relation for the size of the shard key and how do you split the data horizontally across the shards. Yes? I'm sorry, I did not hear that. Yes? Yes. Yes, so for the question is, the config servers are running as a replica set, and can we do a rolling upgrade for the config servers? Yes, that's how we upgrade MongoDB replica set, whether it's a replica set that stands for a shard or a replica set that stands for the config servers. With MongoDB, the upgrades for our replica sets are that we first upgrade all the secondary nodes. At the end, we step down the primary and then upgrade the former primary node which after the step down will be a secondary node. Another important configuration for replica sets is that you can have different value for priority, and when the replica set is on the same state, the data is on the same state, the node that has the higher priority will hold an election, and it will say, I have priority 100, you guys have priority 1. I want to hold an election, I will be the new primary. Until that node becomes the new primary, it will hold elections all the time. Anything else? Okay, thank you.